Hello, and we are going to prove a theorem from the textbook. This is Theorem 5.55, and what this theorem says is that let T from V to W be a linear transformation where V and W are subspaces of Rn. Suppose the dimension of V is M. Then what we have to prove is M is equal to the dimension of the kernel of T plus the dimension of the image or the range of T. So some vocabulary you should know before we go ahead and solve this problem. Make sure you know what a linear transformation is. Know how to show that something is a subspace. And then you should also know what the dimension, the kernel, and the image of a linear transformation is. So let's decide what we are proving. What's our if? What's our then? So our if A, our statement A, is that T from V to W is a linear transformation. Where V and W are subspaces of Rn. And we also know that the dimension of V is M. That's what we're given. And then what we need to prove is part B. And that's just the statement that M is equal to the dimension of the kernel of T plus the dimension of the image of T. Okay, there's a proposition in the book that we're going to use, and this proposition tells you when you can say that something is a subspace. So we're going to show that the kernel and the image of T are subspaces. So I've already worked out the forward-backward process, and let me tell you, this one is a more complex proof. There are more steps involved to prove this one. So sparing you the details, I'm just going to give you the steps that we're going to go ahead and use to prove this statement. So after statement A, we know that we have a linear transformation. V and W are subspaces of Rn, and we also know that the dimension of V is M. Our first step, A1, is going to have us use the definition of a subspace, and there's a proposition in the book. It is proposition 5.52 to verify that the kernel of T and the image of T are subspaces. And that's going to be of V and W respectively. So the kernel is a subspace of V, and the image is a subspace of W, respectively. Okay, once we do that, then we're going to use another theorem and a corollary. If we know that something is a subspace, then we can show that they're a span. And I'll just write this up here. So A2, from A1, now we go to A2 by theorem 4.87 and corollary 4.88, subspaces are spans of linearly independent vectors. And then what we're going to do is we're going to find subspaces of the kernel of T and the image of T to build a basis for each one. To build a basis for each. And that is going to connect with going backwards. If we started with B, we go backwards. That is B3. This is where we also build a basis. Find a basis of the image of T and the kernel of T using the definition of basis. And what are the two things that need to occur in a basis? Well, the first thing is that they span the space, and then the second thing is that they are linearly independent. Okay, then we get to B2, and we're almost there. B2 is going to apply the transformation T to the basis, and we want to show that by adding the transformed basis, that forms a basis for V. Show that. Adding the transformed basis for the kernel of T and the image of T together forms a basis for V. And we'll use one of the properties of linear transformations. T of V1 plus V2 is equal to T of V1 plus T of V2. And then finally, we know that the dimension of V is M, so we'll just call it the dimension of V. The statement we want is that the dimension of V, we know that that's also known as M, is equal to the dimension of the kernel of T plus the dimension of the image of T, and that comes right out of the previous statement. Okay, so spend a minute to kind of understand our process and how we're going to go about this proof. And then we're going to prove it. So let's get to the proof. Here is our proof. By proposition 5.52, the kernel of T is a subspace. That's what the proposition says. A subspace of V, and the image of T is a subspace of W. Okay, so now that we know that they're subspaces, we can find things out about them, including creating a basis for each one. So let's start with the image of T. Consider a basis for the image of T. So we can create a linear transformed, remember the image is just the outputs, the set of outputs. So we can create a list here. Let's say our vectors are v1, v2, v3, all the way to vr. So the images will be T of v1, T of v2, all the way to T of vr. So we'll consider that there's R items in that list. And then let's also consider a basis for the kernel. Remember, the kernel is just the set of the inputs, or that cause the linear transformation to be equal to 0. So we'll do the same thing. Consider a basis of the kernel of T. And we'll just create a bunch of vectors. We'll call it U1, U2, all the way, and then we have maybe a different amount in there. Let's just use US, U sub S. Okay, so now we're going to use the definition using the linear transformation and linear combination, and we're going to go ahead and start finding the kernel of the linear transform matrix. So for any vector v, which is in our input space, capital V, there exists scalars C sub I such that the transformation T of V is equal to the sum from I equals 1 to how many things are in the image? R of Ci T of Vi. So we're just representing the outputs as a linear combination of the vectors in V. And then from there, we're gonna set this thing equal to 0. So I will subtract the sum from both sides, T of V minus the sum from I equals 1 to R of Ci T of Vi. That is equal to 0. And then we can use that property, the property about linear transformations. I'll give you the little, put this in maybe in parentheses here. T of V1 plus V2. So if we add two vectors inside the linear transformation, and then we multiply by T, or do the transformation, that is equal to the transformation of each vector respectively added together, T of V1 plus T of V2. So if I go ahead and it's almost like factoring out or taking the T outside. So instead of going from the left side to the right side, we're going from the right side to the left. We're going to replace this with T of V, and we could just be adding a negative here. T of V minus, right, plus a negative would be minus the sum from I equals 1 to R of Ci T of Vi. And that is equal to 0. So that just follows from the previous step. And what do we call this? The set of outputs where the transformation is equal to 0, the inputs. If we plug these things in and we use our transformation, we get 0. This set of inputs is called the kernel of T. And by the definition, right, that is what a kernel is. By the definition of kernel, V minus the sum from I equals 1 to R of Ci Vi is in the kernel of T. And we know, going back up here, we have our basis of the kernel of T, which means that we can write the one down here as a linear combination of those in the basis. So now we're showing a relationship between the vectors in V and the vectors in the kernel. So hence, or we can use, whatever language you want, hence, we can write a linear combination with scalars, and we'll just choose a letter here, AI, scalars A sub I, such that the result we got in the kernel up there, V hat, use the blue color that I did, V minus the sum from I equals 1 to R of Ci Vi is equal to the sum from, we'll use, instead of I, I'll use a different subscript J. J equals 1. And then how many of them are in here? How many are in the kernel? There's S of them. So we'll go to S of A, J, U, J. So now we have a relationship between the two sets of vectors. And what that means is we can move the one on the right to the other side. And as a result, V is equal to the sum from I equals 1 to R of Ci Vi plus, right, when I move it over, I'm adding it, the sum from J equals 1 to S of AJ UJ. And what's true about all this? This whole thing is 0 only when all of the constants Ci and Aj are 0. Thus, V, the vector set, is equal to the span of the vectors. So if we have a linear combination of pairs of vectors, we can take each one from the first sum and each one from the second sum, and they will span the entire space. V1, V2, all the way to VR, and U1, U2, all the way to US. And I should have said, if we set this equal to 0, the only way that's going to be true is if all of the constants Ci and Aj are equal to 0. If we can show that the vectors, if we can show that the vectors v1, v2, all the way to vr, and u1, u2, all the way to us are linearly independent, then it will follow that this set is a basis. And it's a basis for what? It's a basis for the m-dimensional subspace. Which we defined as phi. Okay, so correct what I said earlier. This is not equal to 0, but we're going to set it equal to 0. And once we set it equal to 0, we have to show that in order to be linearly independent, that all of the constants have to be 0. So that's something we have to show. We have to go through that process. So we're going to suppose that we have the linear combination above, the sum from I equals 1 to r of ci vi plus the sum from j equals 1 to s of aj uj. Suppose that that is equal to 0. And in order to show that the vectors are linearly independent, we have to show, by doing that, we have to show that all the CIs and the AJs must be 0. That's the definition of a linearly independent set. Okay, so what do we have here? We can do a linear transformation. We have our equation up here. We are setting it equal to 0, just like we have down here. And from there, we can apply the linear transformation to both sides. Applying the linear transformation to both sides. We will take t of the left side. We get the t of the sum from I equals 1 to r of ci vi plus the sum from j equals 1 to s of aj uj. And that is equal to t of 0. Okay, we're going to use the property that we used above, which is the one where we split it up right here. We'll use this property. Using properties of linear transformations, we can rewrite the left-hand side as t of the sum from I equals 1 to r of ci vi plus t of the sum from j equals 1 to s of aj uj. And then we know that when you plug in 0 into the transformation, we should always get 0. So that's just a natural result of that. And then we can also use another property. We can bring the t inside of the sum, because if you add up a bunch of transformations, that's the same as taking the transformation or summing, taking the transformation of a bunch of sums is the same thing as adding up each transformation. So it's almost like we're putting the t inside of the sum. That is equal to the sum from I equals 1 to r of ci t of vi plus the sum from j equals 1 to s of aj times t of uj. And that is equal to 0. And if you remember what we did earlier, this thing on the left-hand side is really just the same thing as t of v. That's something we defined way earlier in this problem. You can rewind to find it. So all we really have to show, we already know the left-hand side is true, we have to show that the AJs are all equal to 0. The only way this will be true is all of those are 0. Since we mentioned earlier that t of v1, t of v2, all the way to t of vr, those are linearly independent. By the definition, it follows that all the ci's are 0. So that's something that we defined earlier. And we also know that, like I showed above, the sum from I equals 1 to r of ci t of vi, we can just replace that with t of v. And we also know that the sum from I equals 1 to r of ci t of vi plus the sum from j equals 1 to s of a j u j is equal to tv. The only way that can be true is if we have something that is equal to something on the other side. We know that these two are equal. The sum from I equals 1 to r of ci t vi, we know that's equal to t of v. And the only way that can remain true is if this in the middle is set equal to 0. So thus, the sum from j equals 1 to s of aj of uj is equal to 0. And as we defined earlier, since the vectors u1, u2, all the way to us are linearly independent, that must mean, or that means, that all of the AJs must be equal to 0. So what have we just proved? We have just proved that we have shown that the set u1, u2, all the way to us, and the rest of the vectors v1, v2, all the way to vr, this set is a basis for v. And what's the size? How many vectors are there in this basis? Well, you go from 1 to s, So there's S of the U vectors, and then from 1 to R, there's R of those. So that's S plus R vectors. Okay, so what do we know about the dimension of V? Here's our conclusion. The dimension of V, we know that that is equal to M. And we also know that by showing the above, that is equal to the dimension. What was the set of S vectors? That is the kernel of T. And we add that to the set of vectors in the image, which has size R. And now we have the fact that M is equal to S plus R, which is exactly what we were trying to show, that the dimension of Vm is equal to the dimension of the kernel of T plus the dimension of the image of T. Our proof is done. Thanks for watching.